Welcome to the deep dive. Today, we're taking a closer look at a really fascinating area of engineering. It's
hmm
all about advanced materials and how they're making modern aircraft not just stronger, but also, significantly lighter. We're going to unpack some really cutting-edge research.
Indeed. And our focus today is on a specific study, quite groundbreaking actually, that delves into polymer composite materials.
Mhm.
You might hear them called PCMs.
PCMs, right?
And their role in aerospace engineering is just transformative.
Mm.
These materials offer incredible strengths for their weight, but using them effectively, integrating them, well, that poses unique challenges.
Especially joining parts together.
Exactly,
Yeah.
especially how different parts, sometimes different types of materials are joined.
Okay, so our mission for this deep dive is to give you a clear, sort of concise understanding of how engineers are tackling one of those really critical challenges. How to connect these composite structures to, say, metal parts in a way that's just incredibly reliable. We'll explore the clever ways they design these connections, how they stress test them, push them to their limit.
Even peek inside them.
Yeah. Using advanced imaging to see exactly what's happening, like right down at the microscopic level. Get ready for some surprising stuff and hopefully a few real aha moments.
Very interesting.
Okay, let's start with the basics then. These polymer composite materials, PCMs, they sound amazing. Our sources say they can be, what, 4 to 5 times stronger than traditional aviation aluminum?
That's the ballpark, yes, in
What?
terms of specific strength.
So if they're so strong and light, why aren't all new planes just made entirely out of them? Seems like a no-brainer, right, for weight reduction.
Yeah, that's the core paradox, and it's a really good question. While their specific strength, so strength per unit of weight is incredibly high, the polymer binder,
The glue holding it together. Essentially, yes. The binder holding the reinforcing fibers often has lower deformation and strength properties compared to the fibers themselves.
okay.
So this means they're really impressive mechanical properties of those fibers. They're only fully realized in very specific directions along the fiber.
Right.
Traditional designs, like a simple flat sheet, can't always tap into that full directional potential. So you don't always get the kind of mass reduction you'd intuitively expect.
That clarifies it. It's like having super strong threads, but if the stuff holding them isn't quite as good, or if the design doesn't line them up right for the load.
Exactly. The whole structure isn't optimized.
So what's the clever solution? How are engineers getting around this to really leverage those strong fibers?
Well, one of the most promising approaches is something called pro-composite structural design, and specifically using isogrid structures.
Isogrid.
Think of them as spatial mesh structures. They're formed by intersecting stiffeners or ribs.
So instead of just a solid sheet, the load-bearing bits are strategically placed along what we call geodetic lines.
Geodetic lines. Can you break that down a bit?
Sure, think of it like the shortest path between 2 points on a curved surface. Like an airplane's flight path on a globe often looks curved on a flat map, right?
Yeah.
But it's actually the most direct route. So for a cylindrical fuselage, these lines might look like helical spirals and circles.
Ah, okay. Following the curve efficiently.
Precisely. And this design maximizes the PCM advantage by aligning the main load paths with that strong fiber orientation. Make sure the fibers are doing the heavy lifting.
Very elegant. Focusing the material where it counts. And you mentioned these aren't totally new ideas. There's some history here.
That's right. The concept's been around. The Vickers-Wellington aircraft famously used an isogrid structure way back, but with metal.
Wow, okay.
Then jump forward to the 1980s, and we saw composite isogrid samples being developed. Think Boeing B757, B767, even a demonstrator for the Soviet IL-114.
So it's been tested for a while.
Definitely. And today, lots of projects for future civil aircraft are really focused on composite isogrids because they demonstrably offer higher strength, better rigidity, and crucially lower weight than traditional designs. It's a proven concept, getting a boost from new materials.
It's fascinating, that evolution. But, okay, you have these amazing composite panels. How do you actually join them? Join them together or connect them to other bits of the plane, especially metal parts. That sounds like a potential weak spot.
Absolute critical point.
Yeah.
And that's exactly where these things called metal-composite detachable joints, or MCJs, come in.
RCJs.
Yep. They're vital for unifying individual components into the larger airframe. And our deep dive today, it centers on a specific and actually relatively understudied type of MCJ, one that uses a composite loop element.
A loop.
Yeah, previous research looked more at, standard bolted joints or adhesive joints, but this study really zooms in on the strength and, importantly, the damage development in this specific looped joint design when you pull on it under tensile stress. It's filling a knowledge gap.
Okay, let's talk about this loop then. What makes it special? How did they design it to handle these huge forces? This sounds like the engineering magic.
It's pretty neat. The prototype joint they studied uses a main composite part shaped like a closed loop. It's made from unidirectional carbon fiber using something called tape winding technology.
Tape winding, like wrapping tape.
Sort of, but very precisely controlled. Now, the loop has a constant height, 30 millimeters, but, and this is key, a variable thickness. It ranges from about 6.5 millimeters up to 10 millimeters.
Variable thickness, that sounds very deliberate. Why do that?
Totally intentional, and it's a really key design innovation here. The thickness reduces in what they call the minimum cross-section.
Right where it meets the metal part.
Exactly. It goes from 10 millimeters down to about 6.4 millimeters, right at that critical contact zone.
Yeah.
And how they achieve this is clever. They actually compress the material during manufacturing in that specific area.
Compress it.
Yeah. This local compression reduces the percentage of the polymer binder, the epoxy, and effectively increases the local strength of the composite right where it needs it most, at that point of contact.
That's brilliant. It's like built-in reinforcement, densifying it right there.
Precisely. It's about optimizing the material locally.
So they must have calculated all this beforehand. This wasn't just trial and error.
Oh, absolutely. They use detailed design calculations and finite element method modeling, FEM.
FEM, right. Computer simulations.
Exactly. To figure out the maximum destructive loads and map out the stress and strain inside the joint. For the material, they chose high-performance carbon fibers IMS65 from Toho 10X with an epoxy binder.
And the calculations showed?
Well, they use a simplified rule of mixtures for initial estimates. And that showed the tensile strength in that minimal section, the compressed part of the loop, was calculated around 300 and 629 megapascals.
Okay.
Which is roughly double the strength of the regular uncompressed section, which was about 1863 megapascals.
Wow, double the strength just from that manufacturing tweak. So they intentionally made the most critical point twice as strong, at least on paper. How did that translate into their testing plan? What load did they aim for?
Those calculations guided them to set a maximum design tensile load, they call it Pmax, of 250 kilonewtons for the experiments.
250 kilo-N.
Right. And what's also interesting is that this 250 kilo-N figure was actually 3 times lower than what purely theoretical calculations just based on the minimum area would suggest.
3 times lower, so a huge safety margin built in.
A very significant safety margin, yes. Partly because the specific composite they used wasn't fully certified, so they were being cautious, clearly prioritizing reliability.
Okay, so clever design, careful calculations, built-in safety margins. Now, for the moment of truth, they actually made this thing and pulled it apart, right? What happened?
They did. The main goal was just to see how that tensile load affected the composite loop. They used a big testing machine, an LTTM-1000, and just gradually ramped up the load.
Slowly pulling.
Right. First, an initial pre-stretch, just to take out any tiny gaps in the setup. They've measured those at about 0.6 to 0.8 millimeters, quite small.
Okay.
And in those initial loading stages, everything looks good. A nice linear relationship between the load applied and how much the joint stretched.
Which means?
Which is a good sign. It means no significant damage was happening yet. The joint was behaving predictably, elastically.
But they didn't stop there, of course. What happened when they pushed it harder?
Nope. They loaded the sample up to 200 kilonewtons, which was 80% of that calculated Pmax.
Okay, getting close.
And then they went beyond Pmax up to 300 kilonewtons, which was 120% of the design load.
Pushing it into the red zone.
And at loads over about 260 kilonewtons, they saw a definite change. The nice straight line on their graph started to curve, a deviation from linear behavior.
Meaning?
Meaning things were starting to happen. Sure. It indicated the initial destruction of the composite element. And, importantly, they also observed plastic deformation starting in the metal bolts holding the joint together.
Ah, so the metal bolts started to permanently bend or stretch at the same time the composite showed initial failure signs?
Around the same load level, yes.
What does that tell us? Is that good or bad?
That's actually crucial, and it was good news for the designers. The experimental results confirmed their design requirement. The composite tape should only begin to fail after the metal bolts start to yield, to deform plastically.
So the metal acts like a sort of fuse.
In a way,
Yeah.
it demonstrates they successfully built in those extra strength reserves for the composite part. They were aiming for what engineers call an equal strength joint, where no single part is dramatically weaker than the others. Ideally, things yield gracefully together.
Makes sense.
And their FEM modeling, remember that predicted a safety margin of 3 in that minimum thickness zone.
Yeah.
Well, these experimental results strongly supported that prediction. It shows the design was robust.
It really highlights the power of good modeling backed by testing. Now, you mentioned they used advanced FEM, a nonlinear approach. Why was that important? Why not just a simpler linear model?
That's a great point. For these kinds of complex joints, you've got high stress gradients, you've got very different materials, the composite and the metal behaving differently.
Right.
A simple linear model,
Right.
it can give you significant errors in that situation.
Yeah.
Just assumes everything stretches proportionally to a load, which isn't always true, especially near failure.
So the nonlinear model?
Their research used a newer nonlinear engineering method. It solves the problem iteratively, step by step, accounting for both physical nonlinearity, like the material properties changing under load,
Yeah.
and geometric nonlinearity.
Geometric, like the shape changing affects the stress.
Exactly. And the experimental stress strain diagrams they recorded, they showed really good agreement with these more complex nonlinear calculations. It confirmed the structure showed what they called weak nonlinear behavior.
Which is good.
Yes, it validated its high strength. What's really interesting, and something the linear model would miss, is that as the tension ramps up, the fibers inside that loop actually straighten out a bit, and this straightening increases the stiffness. Plus, the stresses on the inside and outside surfaces of the loop start to equalize because of these small shape changes.
Yeah.
It's like the joint subtly reconfigures itself to handle the load better.
That's fascinating. The material itself is responding dynamically.
Precisely.
Okay, so we see the overall strength, how it behaves under load, but what was happening inside the composite material at that micro level? How did they see damage that you couldn't spot just by looking?
Yeah, this is where the really cutting-edge non-destructive testing comes in. They used high-resolution acoustic microscopy, or AM.
Acoustic microscopy using sound waves.
Exactly. Very high-frequency ultrasound, in this case 50 megahertz. They used a focused probe to create 3D images, scanning with tiny steps, just 25 micrometers.
Wow, that's detailed.
Extremely. And this allowed them to meticulously compare the macrostructure before loading and after loading, layer by layer. It's like having X-ray vision for the material's internal structure without cutting it open.
So what did the AM show initially, before they applied any major load? Was the material perfect inside?
Well, the initial scans, specifically the C-scans, which give you that top-down map-like view of internal layers,
Okay.
they revealed what the researchers called a relatively loose PCM structure right there in the contact zone, even though it had been compressed during manufacturing.
Loose. So the compression didn't make it perfectly solid.
Apparently not entirely. They found numerous technological defects. Basically, small irregularities in cavities, sometimes pretty long, like 7.5 millimeters and maybe 0.75 millimeters wide,
Wow.
located along the bundles of reinforcing fibers, essentially spots where the adhesion between the carbon fibers and the epoxy resin wasn't perfect. So no, the starting material wasn't perfectly uniform.
Okay, so there were these tiny imperfections baked in from the start. What happened to them when the joint was loaded up to 200 kilon and then that higher 300 kilon load?
This is where it gets really fascinating, quite unexpected. The acoustic images show that under load, as the fiber structure deforms, these technological defects actually migrated.
Migrated. They moved.
They moved. For example, they saw defects that were visible at a depth of 0.25 millimeters in the initial scan. Well, after the 300 kilon load, those same defects were now seen at 0.20 millimeters depth.
So they shifted 50 micrometers towards the edge.
Exactly, towards the free edge. And what's more, some of the initial fuzzy spots, the inhomogeneities they saw as light strokes in the images, they actually disappeared after the 200 kilon unload.
Defects disappearing and shifting.
Yeah.
That's really counterintuitive. What's causing that? It's not just breaking down, is it?
No, it seems to be something else entirely. This is a really profound insight, I think. The material isn't just passively taking the stress. It seems to be reorganizing itself at this micro level.
Reorganizing.
Yes. The study concluded that the increased external load and the compression it causes in that contact zone contributes to the compaction of the composite structure. Gets squeezed tighter.
And they could measure that.
Directly. They measured the loop's thickness in that maximum loading zone. Remember, it started at about 6.4 millimeters. After 200 kilon in, it went down to 6.15 millimeters. And after the full 300 kilon in, it was down to 5.8 millimeters.
That's quite a squeeze.
It is. They calculated it as a 1.1 times compaction. And this compaction, this reduction in internal voids and looseness, also caused the acoustic images to get less contrasty. The material literally became denser and more uniform under load.
So instead of just cracking, it's almost like it's healing itself, or at least optimizing itself.
That's a strong way to put it. But yeah, it seems to be actively adapting to the stress, compacting, rather than just developing cracks. That's a huge shift in thinking.
Absolutely incredible. So it became denser, more uniform. Was anything else happening down there? What about the binder, the epoxy?
Yeah, something else was seen. The B-scan images, these give you a cross-sectional view, like slicing through it.
Right, like looking at the layers sideways.
Exactly. Those showed that as the load increased, the surface of the specimen in the contact zone became rougher. And this was due to the extrusion of the polymer binder.
Extrusion, like it was squeezed out.
Literally squeezed out. The epoxy resin was being pushed out from between the fibers in that zone of maximum compression where it contacts the metal part.
Like squeezing water from a sponge.
That's a good analogy. They actually measured a little ridge protrusion about 0.17 millimeters high and half a millimeter wide at that maximum 300 kilonewton load. It just shows how dynamic things are. Even the matrix material is moving.
Wow. This has been a truly, truly deep dive. We've gone from the big picture of lighter, stronger aircraft down to the microscopic movements of defects and binder material.
It really connects the macro performance to the micro behavior.
We've seen how clever design, like that variable thickness loop, combined with precise calculations and really intense testing, and then this amazing acoustic microscopy. It's all pushing the boundaries.
Definitely. So, to recap the key findings. This study showed a really effective engineering technique for designing these metal composite joints, their composite loop. It absolutely had the required tensile strength.
Check.
The experiments matched up well with those complex nonlinear calculations.
Double check.
And crucially, the acoustic microscopy confirmed the carbon fiber structure itself wasn't fundamentally damaged, even when loaded 20% beyond its design maximum.
Which is impressive resilience.
Very. Instead, what happened was this significant compaction, that 1.1 times reduction in thickness, plus the slight migration of those pre-existing defects, and that squeezing out of the polymer binder.
But no new cracks or fiber breaks.
No other material damage was detected. And that makes sense because the actual stress applied was still only about 30% of the composite's ultimate calculated strength limit. It showed its resilience and this unexpected dynamic response.
So, wrapping this up, what does this all mean for you, the listener, and maybe for the future of engineering?
Well, this whole approach, studying damage, or rather material changes, at these very early stages of loading, is incredibly valuable, especially for designing things like these lattice composite structures, where reliability is just paramount.
It's about understanding that resilience, not just the breaking point, seeing how it adapts before it fails.
Exactly. It's about building in that robustness by understanding the material's dynamic response.
Which leads to a really interesting final thought, doesn't it?
It does. If we can actually observe these micro-level defects shifting, even disappearing, and the material compacting under stress without catastrophic failure, what does that imply?
Where could that lead?
Could we eventually design materials that don't just resist damage, but maybe actively adapt? Or even, dare I say, self-optimize their internal structure in response to the loads they experience during operation?
Making them even more robust, maybe longer lasting than we currently imagine.
Perhaps.
Oh.
Or is this compaction just a temporary phase? Is it perhaps delaying a different, maybe more severe form of damage in the very long run? We don't know yet.
Definitely something to ponder. Maybe next time you're on a flight, looking out at the wing.
Think about the materials working and maybe even rearranging themselves down at that tiny scale.
A fascinating thought to end on. Thanks for that deep dive.
My pleasure.